volume, so I might have to edit that one later on. But yeah, so let's just have a look at what we have so far. So today we're going to be looking at Michael Young's double slit experiment and also analyzing diffraction gratings. Now, double slit experiment and diffraction grating, they will yield the same kind of interference patterns. So we will talk about how they look similar and how they look slightly differently from each other. You then have the dot point requirement, which is we need to analyze this double slit experiment and diffraction gratings quantitatively. What we mean by quantitatively is we want to see this in numbers. So what does the numbers tell us about this whole experiment? Now, ideally, we should be trying to conduct this experiment ourselves, but I'm not sure if we have the equipment, but if we do, we'll try that in the coming weeks as well when we have time, after we've caught up with some theory as well. Okay? So this is the experiment we're going to be looking at. We are looking at the interference of light using double slit apparatus and diffraction gratings using this formula here. Okay, there were some really good videos from Rotasium about this double slit experiment, which I will later on link into the classroom. So if you do want to look into it a little bit more, by all means you can do that as well. So let's just quickly recap what the interference patterns look like. Remember, if it's constructive interference, so where you see all these bright spots, that's where two cresses come together, and that's where two troughs come together. Okay. In terms of physics, we call these waves combining in phase with each other. So they are coming at the exact same shape as each other. They're coming at the exact same shape as each other in the same degree of time. Okay, so exactly the same two waves coming together. Then we have destructive interference, where you have a crest and a trough coming in at the opposite time period to each other, and they essentially cancel each other out. So I can have one wave that's coming like this, and then I'll have another wave that is what we call coming out of phase to this wave, and as you can see, the resultant wave would cause some kind of cancelling out between these two. Okay. Last lesson, I commented on a thing called nodal lines. So an area on the interference pattern where no motion is occurring. So this black spot, so these dark spots here, this is what we mean by the nodal lines. Okay. So this is where during a interference, you won't see any surface motion of the wave. That's what we mean by the nodal lines. Okay. Now, back in the 1800s, there was a guy called Thomas Young, and he did a little experiment where he had a little candle, he had a piece of hair, and he looked at the piece of hair through the candle. So if you think about it, you have a piece of hair, you just put it right dead center of that flame, and he looked into the flame to see what was occurring. Now this was by his time, Newton already showed, or Newton's corpuscle theory of light was already highly accepted. So a lot of people already had the belief that light was a particle. He was trying to show that as well, but he found some other interesting factors. So he put his piece of hair in front of the candle, and then he saw a little interference pattern. So instead of seeing the light just scatter in all directions, he found that there was a beautiful colored pattern parallel to the piece of hair. So he had, let's assume, some nice little colors, maybe some red here, and then he saw some nice little blue here and blue here. So that's kind of what he saw with his little thing. So the light kind of dispersed out. And you can try it at home as well, assuming you don't pull your hair out. That light, when it goes through some obstacle, it creates this interference or separation of colors. And we know that this separation is diffraction. Okay? So diffraction is where the light is hitting this piece of hair and then it is forced to deviate. Depending on the wavelength of light, it will deviate more than the others. Blue light will always deviate more than red light. Okay? So that's kind of what he realized. Now he went a little bit further. He decided he'll be a bit more inventive. So he decided what he will do. And let's just look at the question. Yep, I'm recording this video right now, Sam, which is why I said ask the question, don't type it. Because if it pops up on the screen, then, just pops up. Alright, so we have Young and his double slit experiment. And in this experiment, it's very simple. So he has a window blind, okay? In the window blind, he punches a little hole, and he has a converging lens. So it'd be convex, I do believe. Convex lens that focuses the beam to make it parallel, so it's a nice parallel beam. That will then go towards a piece of card that has two little holes in it, so that acts as his double slit. What he then finds is these light will join back together, but in this kind of array of interference patterns. So we've been talking about the bright bands and the dark bands. This is what he saw from his experiment, okay? So let's just recap on what the setup was. Firstly, he used a monochromatic light source. For anyone who doesn't know what monochromatic means, it means a light color that's from a single wavelength. So it's a single wavelength or single frequency light. Single frequency light, okay? The reason why a monochromatic light is very useful is because it gives you a more consistent pattern. Remember what I said before, if it's white light that you're using, white light consists of multiple different types of colors, so it will disperse a great array of patterns. If you, well, that bird's not very friendly for the recording. And just for anyone who doesn't know, I am doing this outside, so if you do hear random birds or trains, you know why. So the reason why we use monochromatic light is to keep a consistent pattern. If it is not monochromatic, then you'll see a lot of different bands on the screen, and it'll be very difficult to look at the orders or where the dark and bright bands are. So that's why we use monochromatic light. It's to give us a more clear picture of the different orders of interference that we see. The converging lens behind the hole is to help us make the beam parallel. So that's to make it have a focused beam that we can see very clearly. Okay, awesome. Thank you, Owen, and no worries, Ayush. And so we have light passing through two pinholes. So these are the two pinholes that we're looking at. These will act as the area for the diffraction of my light source. So my light is coming directly parallel towards these two holes here. And then it's going to hit a dent and then it's going to diffract out. So it's going to diffract out again. And then these light sources are then going to reach the band. Some might reach it in the same orientation, so in phase. Some might reach out of phase, and that's what dictates the kind of pattern you see. Now, he initially had the screen about 2 meters away. And so the observed thing you see there is light being overlapped, and you see this kind of effect. So this is like a modern day version replication of his patterns, as you can see. The dark band here is what we call the center point. So if you saw this on a intensity diagram, it would look sort of like this. So we follow the intensities, goes high, and then it comes back low, and then it lows, and then you can see that little light source here. Now, this will become a bit more important later on, but this mode, nodule node, we call this nodule node 0, and we call this nodule 1, and this we call -1 in that case. So they're just in opposite directions, but technically they're all both 1, or maybe that is 1 as well. So they're both like that. And then if you go further out, we call this the node 2. What we mean by node 2 is the second constructive interference pattern that we see on the charts. So this is what we kind of have. Okay. So the antinodes represent constructive interference lines, so everything we see here. And then we have the node lines, which is destructive interference. And like I said, if there is destructive interference here on this black line, you won't see any motion of the wave during this interference. And then the next we have is the observation. So closely packed, you see the fringes of bright and dark spots. And so how did Young explain this? He used this with wave interference. Remember what I said? At this point in time, most of the people accepted that light was a particle. So what he found was in contradiction to Isaac Newton's theory that light was a particle. So he believed that these bright spots occurred similar to water waves, where they come together in phase, they reinforce their amplitude, causing constructive interference. If you see dark spots, that's because the waves are coming out of phase and canceling each other out, causing destructive interference. Okay? So that's a property that waves would have, is what he's saying. Mind you, when he first put this out back in the 1800s, it wasn't very well welcomed, and you'll hear from many of the little stories we talk about with scientists. Usually what they say at the time, and we think is really brilliant now, was not the accepted or welcome norm at the time. So it actually takes quite a lot of effort to convince people that what you have is something worth paying attention to. Okay, so if I try and show you what out of phase kind of looks like, you can see out of phase just means that the two waves don't align with each other. So we have this 90% out of phase, 135% out of phase, and then we have 180% out of phase. Now, for a complete destructive interference to occur, okay, you want the two waves that you are looking at for interference pattern, they should be 180 degrees out of phase to each other. Okay? So if they're 180 degrees out of phase of each other, you'll have a complete destructive interference. So I'll put that up there as well. So that's where you get the actual complete destructive interference. But if you also look at this diagram here, you'll notice something really interesting as well. And it becomes pretty important when we talk about the formula later on. If you have a look here, so we have our wave here, and then we have another wave here. So you can see that when it's 180 degrees out of phase of each other, okay, the second wave is actually half a wavelength further away from the initial wavelength here. So this wavelength here, that completes one wavelength, and then this second wave completes it half a position after it. So if it's 180 degrees out of phase, you can also say it's half a wavelength in difference. Okay, so that's kind of how you get constructive interference. So it's half a wavelength in difference, or 180 degrees out of phase there. So this comes to the actual interpretation of Young's experiment, and this is what we're going to look at. Now, before I go into it, the center bright spot is just the dead center bit that you see. That's usually, obviously, the brightest part you have. In this formula that we're going to look at, we have the first order of brightness, the second order of brightness. What that actually means is when the diffraction pattern occurs, so the light comes through from the light source into our double slit, okay, it's going to join up here to make the central bright spot. This is where you'll see the brightest part. The first diffraction order comes here, or it comes here. So these two parts, we can both call this the first bright spot as N1, and we can call this N2. In between what you see as the dark bands, there is a number we use. We give it as a, not a whole number, but as a decimal, so a fraction. So the destructive part would be 0.5, and then after the first bright order, this would be, let's say, 0.15. Okay, so that's kind of what we're working with here. Let's just try and look back slightly though at looking how can we make sense of what we're seeing. And let's start with this bit here. Okay, so Young realized for light to cause this type of interference pattern, the light ray has to travel from here to here. And then the second ray needs to travel from here all the way to here. Okay? If you look at this diagram really carefully, and I encourage you to look very carefully, there is a noted difference in the length that these rays have to travel. Okay? And the difference is this bit here. You can see the second ray needs to go all the way here, but it travels a little bit longer here compared to the first ray here. Now we can make a little assumption that they're sort of parallel at really long wavelengths, so we're just making that assumption. That's the assumption they make. We're going to say that this is the path difference. Okay? This is the path difference between the first light ray and the second light ray to travel to spot 1 here. And it's because of this path difference between the waves that we get interference patterns. Okay? So what that tells us is I can predict how far this interference pattern is from the center bright point if I knew this separation distance and the angle that's being created between the two slit points. Okay? So X here, we're going to call this the fringe separation. And all that means is it's the distance between the center bright spot to the other next bright spot. Fringe length can be in multiple ways. You'll also see a quantity called capital L. That is the length between our screen and the slits. So I know I'm bombarding you with a lot of info here, so that's why I am recording this. So there you have that. So let's break this down a bit. So the path difference, the formula we're going to use delta for path difference, and we're going to say R1 minus, or R2, sorry, minus R1 will be the path difference. As you can see, R2 has to travel longer, and so that's why we designate R2 as the thing that gets subtracted by R1. So that will tell us the path difference that R2 has to travel in comparison to R1. Okay? In terms of how we determine the angle we're going to use, so the angle we're using is basically the normal line. So between the normal line joining the two slits. So we have this line here, we have this slit here. Imagine you have these two rays going across to its destination. We're saying where these two rays meet as a normal line. So if I drew an imaginary normal line here, okay, so a nice right angle triangle, then the angle from the first slit made to the normal line to R2, that line, that is angle theta. Okay? You might need to replay this point if you're not didn't quite follow that, but just remember when the two rays go towards the screen, if we make a normal line from the slit, so from the first slit, make a normal line here, then we can work out what the angle is that the first slit makes to this normal perpendicular line here. What we also know is that we can assume the screen here, so this is the screen we're looking at, the length of the screen will be perpendicular to where the slit is. Okay, so assuming the screen is also perpendicular to this normal line, okay, so this here, the path difference can be related to angle theta. Okay, so we can then find angle using angle theta. We can work out what the path difference here is. Let me just show you this as a diagram. You have your triangle. Okay, right angle triangle. This is path difference. This is the angle you're looking at. And this D is the slit separation. So if you remember much about trigonometry, the relationship we have here is the hypotenuse and the opposite side. Okay, so using sine theta, okay, using sine theta, I can find that that angle I'm looking at is dependent on the path difference over the slit separation. So if I want to find the path difference, okay, I just move D over onto this side, and I get something like this. So what we have here is path difference, or what we have here is the path difference. What we have here is the slit separation. And what we have here is the angle of the slit to the length of the screen. So there's that. The next thing we know is when constructive interference occurs and when destructive interference occurs. So that gives us a little bit more about the path difference as well. So another thing we know with path difference is this. Okay, if a path difference occurs, so path difference occurs, but the wavelengths are combining in whole number ratios, what that means, might explain this with destructive interference first. Let's say the path difference, the combining of these two waves is one whole wavelength minus a half. Look at the diagram we have here. Look at this diagram here, okay? We have two waves, two sine waves, combining to each other. Can you see that this wave is half a wavelength early compared to where this wavelength begins? Okay? So this wavelength here is delayed by half a wavelength. That's why we can say that destructive and a complete destructive interference will occur when one wave, okay, whatever wave we're looking at, we could say the first one or the second one, so this is just the magnitudes of brightness, is combined with another wave that's half of it. So we're still looking at the same wave, okay, so the wavelength will be the same. This will be the same because we're using the same light source. However, one wave will come in 180 degrees before the other, or we can say it's half a wavelength earlier than the second wave, and that's why we create destructive interference. If it's constructive interference, okay, they will combine in whole number ratio. So let's say the first wave looks something similar to this, okay, looks like that. Now, it doesn't have to meet at exactly the same starting point. It could meet later on. So let's say the second wave comes down here. So it comes like this. So you can see that this blue wave here has been delayed by a whole wavelength because a whole wavelength has already occurred. Okay, but they're still in phase with each other. They're still going to cause constructive interference. So that's what we're going to say. So if we have one whole wavelength, okay, we're going to get constructive interference. If we have half a wavelength combining, we're going to get destructive interference. And that's the main difference between what's happening here and what's happening elsewhere. Okay, this becomes really important because this actually helps us work out path difference as well. If you imagine, if we have destructive interference, okay, in destructive interference, let's just change the yellow. In destructive interference, we already said that the difference lies in half a wavelength. So we know that in destructive interference, the path difference between the two waves is this value here, okay? Half a wavelength early or later. If we're looking at constructive interference, the path difference between the two light rays is just this value here. So if the waves come in the same phase, right, you just rewrite this together. So that's the main difference. Hopefully you understand that. And so we have that. Now, I also said already in the formula, this is equal to n0 because this is the center point. And then anything goes higher will be, and this is for the bright spots, so constructive interference, n1, n2. Okay? L here is the length of the screen and the slits. So I can rewrite my equation like so. Okay? So we can say that the path difference, so this all equals to path difference. The path difference for the first ray and the second ray is found using the formula d sine theta or n times lambda, where n can be 1, 2, 3, how many other orders of magnitude you want it to be. The other thing we find is that at really small angles, sine theta is approximate to tan theta, and we know that if I want to work out the fringe separation, so fringe separation is this bit here, x, okay, we know that tan theta is equal to fringe separation over length of screen, so that, which if we said that tan theta is similar to sine theta at small angles, then we get this relationship here. Okay, so the angle caused by the slit and the normal line is given by n lambda over d equals to fringe separation over length of the screen. It's a lot of information to get in and do understand, but that's what we're looking at. So the formula for constructive interference would be this one here. Okay, Remember, n is the node number. Okay, so that's just where the bright spots are. Destructive interference, we have this. And then the length between interference pattern, which is this one here, you can rewrite the equation like so. Okay, so these are the three equations we're kind of looking into. Distance separation, remember anything that's a distance, okay, need to be converted into meters. Meters and meters, okay? So the first set of questions I'm going to have you look at in this PowerPoint is how does the wavelength affect the fringe separation between the bands? So if we're looking at the first bright spot from the center bright spot, how does changing the wavelength of light cause this? And this I will try and make a separate video of answering these questions, so you can have a look a bit later on. The next one I want you to look at is, what about if you change the slit separations? How does that change the fringe separations of the bright spots? Third one is, what's the effect of the distance of the screen? So distance of the screen is capital L we're looking at. If we change capital L, calculate the fringe separations of the bright spots. And then what I want you to do is show what does that tell you. So how is X in question 6, how is X related to wavelength here? Well, you can see from just purely the equation, you should be able to establish that the wavelength is directly proportional to fringe separation. So if you increase the wavelength of the wave you're looking at, you should see an increase in the fringe separation of your interference pattern. Some more questions and some more. So there's plenty of questions for you to try, plenty of calculations. The last one we're looking at is diffraction grating. This is what it looks like. Okay, looks might be slightly deceiving. We might have this at school, and we can probably try out the experiment as well. So what is this thing? Now, a diffraction grating separates colors or light into its colored components. If it's monochromatic, so if we only have one wavelength of light, then it will just separate it out accordingly. Okay? Inside this grating, you might not see it, but there's some really fine little parallel lines that act as little slits inside the diffracting grating, and it actually spreads the light into different positions. If you compare the diffraction grating and a double slit experiment, you can see there's a very big difference in the sharpness or resolution of the image. So the bright fringes produced by a diffracting grating are much more narrow than a double slit experiment. Okay? So it's a lot finer, and the reason being is obviously because the lines are a lot more narrow. So difference between diffraction grating and double split, the maxima is a lot more narrow, and it's a lot more sensitive, so you can do some more accurate calculations on that. Double slit, you can see that it's a little bit more spread apart. Intensity will stay the same if you're using the same wavelength of light. Okay, another way, diffracting grating is a set of accurately ruled lines on a glass that produces sharp patterns of maxima and minima. So this is really useful with our analysis of the equation d sine theta and lambda. Okay, so that's helping us to work out the path difference between the light and what's happening there. So really nice sharp patterns. How does it work? So you'll have equally distant parallel lines engraved on glass. Okay, these will act as the slits that allow the light to go through. Now, for this to work, the wavelength of light you use must match the gap of the slit. So if the slit has a gap of, let's say, 400 nanometers, so it has a separation of 400 nanometers, then you must use a wavelength of 400 nanometers or slightly less than that, or else you won't get that pattern. Or it could be slightly bigger. I'll have to check on that, but it needs to be close to this the separation of the slits. The more slits you have, the sharper the image. And so these lines break the wavefront and cause a diffraction pattern to occur. If we look at the calculations of this, so let's say we have a white light source and we run it through a diffracting grating, the center will be white, and then you'll have the rainbows forming there. If you have a look here, if we have a look kind of the displacement of red light and blue light, you can see that blue light being the less energetic, or being the more energetic and lower wave, it actually displaces less, so it has a smaller diffraction angle than the color red. So the longer the wavelength of light you use, the greater the diffraction you'll see from the center point in terms of the angle produced. And we can see that again. So the diagram shows how different or how diffraction splits the wavelengths. Note that the longer wavelengths diffract more than the shorter wavelengths. Okay, so red light will diffract more than blue, so the colors will separate. If the light is white, then a full spectrum of the rainbow showing you the equal maximums and minimums will show as well. Either way though, you'll see a similar interference pattern here. So if we did a single split experiment, we kind of look something like this. And then what we have down here is the double slit interference. And so you can see it will give you the same shape, essentially. So if we just kind of compare these, this is a double slit experiment. This is with a diffracting grating, the interference pattern you see. This is if you're using a single slit interference. Notice they kind of all show a similar shape. Now, diffracting grating has narrower lines, but they essentially show the same amount of intensity graph. So kind of, if we're looking at the single slit and it kind of looks like this, in the diffracting grating, they kind of also show the same shape. Mind you, my diagram is definitely not as nice as that one, but so it shows a similar kind of diffraction. Just a couple more questions for you to have a look at, and that is that in terms of the double split and diffracting grating. So we looked at the double split, we looked at the diffracting grating, how they work. So they work very similar to each other. Diffracting grating only gives you more narrower lines. And then we looked briefly on a single slit diffraction as well. So there's not too much different in those. So yeah, so last thing I just want you all to look at is this final bit here. So diffracting gratings work the same way as a double slit experiment, but with many parallel slits very close together. Okay, so the reason why we get the sharper images is because the slits are more narrow and there are more of them, so we get a more sharper image. Okay, and so that is that.